session of NiO. So I'm Srijit here. So let's continue our discussion about Hubbard U. So I have previously stated about how this PDOS or this periodic density of state can be calculated as a processing step. So after the successful electronic structure calculations, it allows us to identify the orbital configuration. For example, how to determine which atomic orbital are dominant at the different energy ranges in the band structure. For example, if you want to see the states near the Fermi level, which are primarily composed of d orbitals of a transition metal or p orbitals of an anion. So how to analyze the chemical bonding? So by examining the overlap and hybridization of PDOs from different atoms and orbitals, we can gain insights into the nature of the chemical bond in material. For example, a covalent mixing or an ionic character, and how to understand the electronic properties. So this PDOs can help explain the electronic as well as magnetic properties of a material. For instance, a high density of a D state at a Fermi level might indicate the metallic behavior or possibility of magnetic ordering. And how to visualize the hybridization. So by plotting the PDOs of different orbitals on the same graph, we can visualize or we can visually identify the energy changes where the hybridization or the mixing of orbital occurs. So how we can use PDOs with the DFT and this Hubbard U in AMS band engine. So the calculations of the PDOs for a DFT plus U calculation or Hubbard U calculation in AMS band is particularly informative since the Hubbard U primarily affects the localized D or F orbitals. So the PDOs can reveal the effect of this Hubbard on specific orbitals, where we can directly observe how this parameter shifts the energy levels and changes the distribution of the D or F states. For example, I have mentioned earlier about Mott insulator. The U term or the Hubbard term will split the D band into the lower and upper Hubbard bands, which can be clearly seen in the PDOs. So this orbital character of the band gap, which opens due to the Hubbard U, the PDOs can show which orbital constitutes the valence band maximum and the conduction band minimum. And also, the application might be indirectly affect the hybridization between the correlator orbitals and other orbitals in the system, which can be observed in this periodic density of state. In summary, when working with strongly correlated materials in AMS band, DFT plus Hubbard U is employed to obtain more accurate electronic structure by accounting for strong on-site Coulomb interaction in localized D or F orbitals. And the projected density of states is used as an analysis tool to decompose the total density of state into contributions from specific atomic orbitals. So this helps in understanding the orbital character of electronic bands, the effect of Hubbard U on the correlated orbitals, and the nature of chemical bonding in the system. So I have taken this nickel oxide, which is a classical example of a material where the standard DFT is used. So you can see I have just done a calculation with the necessary inputs with an unrestricted calculation, and I have taken the exchange correlation function GGABP86 and a little higher order basis at TZP. So I have just selected PDOs for this calculation which we have mentioned, and in this specific calculation I have never used this Hubbard U. So I need to show you that what is the differences between how we can run a calculation with and without this approximation. So let me show you this output. And I'm just going to the properties to understand the band gap. So this is actually an example of how we can see the band gap information with Hubbard U. And you can see the kinetic energy term, the exchange correlation term, the electrostatic, then potential, and the Hubbard term. And what is the band gap information? How many number of valence electrons, the valence band index, the band spin index, the conduction band index, and the top of the valence band, and band gap in AU, electron volt, and kilocalories per mole. So total a number of 16 valence electrons has been considered in this specific case. And also to brief, in this case, this about NiO, I mean nickel oxide, which is a classical example which I have taken that struggles to accurately predict the electronic as well as magnetic properties. So experimentally, a nickel oxide is an antiferromagnetic insulator with a band gap of around 4 keV electron volt. However, DFT calculations often incorrectly predict it to be metallic or yield as much as smaller band gap. So in the next video, I'll be briefing about how these parameters can be briefed with nickel oxide in a typical example. Thank you.